Screen visible. Shall we start?
Yes, sir.
Yeah. You didn't upload your batchmate details. Is it ready? Your J component details? Is the batches and titles are ready?
Sir, where will it upload?
No, I will say I will create a link. You can upload there itself. Okay.
Okay.
Titles are ready, no? Your batches and titles are ready.
So I don't know about everyone, but for me it's ready.
Okay, thank you. So next part of the last topic of module 2 is half-field network. Half-field network. So half-field network was introduced by Professor John Half-Field, and he is a professor in Princeton University in the Department of Microbiology, and he works in the domain of computational neurobiology and biophysics applications. So Half-Field is a physicist. Half-Field is a physicist. He showed that the models of physical system could be used to solve computational problems. John Half-Field is a physicist. So he tried to show that the models of physical systems, okay, could be used to solve the computational problems. So like, so this may be a simple example, like this may be a magnetic bar with the south and north pole. S represents south and N represents the north pole. So these kind of simple physical model could solve some computational problems. So whenever we say that, or the Half-Field say that the models of physical system could solve computational problems. So how such physical systems are created, or how such physical systems are constructed or implemented. So such physical systems could be implemented via hardware by combining standard components. So what are all the standard components in order to create or in order to implement the physical systems in terms of hardware is nothing but anyway we are going to work in terms of hardware means. So we need to purely depend on electronic components or electronic systems. So here the diagram or the circuit shows here is some of the electronic components are connected, and this particular physical system may be used to solve certain applications. And this parallel lines may be considered as capacitors, and this waveforms may be considered as a resistor symbol, and this may be considered as an what you can call it as amplifier, nonlinear amplifier, and this may be considered as an inverting amplifier. If you have a triangle with this may be considered as an inverting amplifier. So like that, the physical systems can be implemented or can be created in hardware by combining certain resistors, capacitors, transistors, JFETs, MOSFETs, etc., etc. So the importance of half-field network in practical applications is limited due to theoretical limitations of the structure. Why? Because the structure seems to be like this. The structure seems to be like this. So it will be, for a simple system, the structure seems to be simple. If you deal with a complex system or complex computational problems, the structure may be complex or the structure may be clumsy in nature. So the importance of half-field network or half-field nets in practical application is limited due to the limitations of the half-field structure, but in some cases they may form some interesting models. If you try to rearrange the structure, or if you try to rearrange the half-field network, So those rearrangement of half-field network or half-field structure may try to solve certain issues or certain applications. So this half-field network usually employed in binary logic task. Binary logic task in the sense is yes or no pattern. So 0 or 1, true or false, yes or no, like that. So it is used only in binary logic task. Example, pattern completion and pattern association. So whenever I see a particular person, so I can able to segregate that he may be a boy or girl, or he may be a man or woman. So like that, so it is considering as binary logic task. Okay. So that is considered here as a pattern completion and a pattern association problem. So for example, since it uses the binary logic task, the half-field network are used to reconstruct the degraded images from the noisy image. So degraded image from the noisy image is nothing but, so this may be considered as original image. Okay. So this original image is degraded due to some external factors. This original image is degraded due to some external factors. Okay, maybe due to the noise, or due to the aging of the photograph, or due to some other what you can call it as external disturbances, like some sketches, or some prints may be faded, or some prints may be some portion of the print may be disappearing. So all those things may be considered as a degraded image. So now this half-field network, if you give an input of this degraded image, okay, so not exactly as an image, this image has to be converted into a matrix representations, okay, and if you give the input image matrix to the half-field network, it tries to reconstruct the degraded image from the noisy image like an original image. So you can see here, so the reconstruction image somewhat closely relevant to the original image, somewhat closely relevant to the original image. So you can see the other example. So you have an original image like this, and this image, see, this is a full image or complete view of this particular cartoon, and this may be a half view or a partial view of this particular cartoon. And with this noisy image or degraded image, we are trying to reconstruct similar to the original image. So that's why they call it as it uses a binary logic task. Okay. The concept of half-field networks, concentrates on these three parameters, or concentrates on these three functionalities. So one, we call it as basics of attraction. Next one is we call it as trajectories, and the next one we call it as attractors. So basics of attraction is nothing but, so if you consider a particular location, or if you consider a particular place, you consider a particular location or a place, you consider this bounding rectangle box. Inside this bounding rectangle box, I have three basins of attraction. So one, this particular red color dots in the top, and other this particular red color dots which separates the other two regions. So this may be considered as region number 1, and this may be considered as region number 2, and this may be considered as region number 3. So we have three regions, and these three regions are considered as basins of attraction. The next one is nothing but the trajectories. Trajectories is nothing but within the attraction region, okay, within the attraction region, we have certain trajectories. Based on those trajectories, these attraction regions are formed. And in order to yield, or in order to group the trajectories, or in order to identify the basins of attractions, we need a certain central point, or we need certain central focus that may be considered as attractors. So this smaller circle is considered as attractors for this region 1 and attractor for region 2, and this is attractor for region 3. So first one is attractors are there. So based on the attractors, okay, some trajectories will be formed. So what particular features are attracted by, sorry, what particular trajectories or features are attracted by these attractors, and this forms a particular basin of attraction. So the particular concept of half-field network lies in these three parameters or in these three factors. One is basins of attraction, next one is trajectories, and the next one is attractors. In the beginning of 80s, Haffield is a physicist. So he published two scientific papers which attracted the entire global scenario that we can able to include the concept of half-field network in the domain of neural networks. So in the year 1982, the neural networks and physical systems with emergent collective computational abilities. So that was the first paper which has been published by John Haffield in the year 1982, and subsequently in the year 1984, so he published another paper, neurons with a graded response or collective computational properties like those of two-state neurons. So both these papers paved the way to include or to consider this half-field network in the domain of neural network, which belongs to the computational intelligence platform. So this two papers was considered as the starting point of new era of neural networks, which we are using these half-field networks to solve certain computational problems. So this half-field network takes the inspiration or obtains its what you can call it as the ideology, or obtains its working principle from the dynamics of brain computation. So the core question here with respect to the dynamics of brain computation here is how is one to understand the incredible effectiveness of a brain in tasks such as recognizing a particular face in a complex scene. For example, you are entering into a particular environment. In this particular environment or particular area or particular location, for example, a mall or a beach or a shopping complex or a festival location. So you need to identify your friend, or you need to identify your father, or you need to identify your brother, whoever may be. So how is one to understand the incredible effectiveness of a brain in tasks such as recognizing a particular face in a complex scene? So the festival location, the mall, the shopping complex, everything is projected or everything is considered as a complex scene. So in that complex scene, so we need to recognize or we need to identify my relatives, my friends, or my well-wishers. So in such cases, so how the brain functions and how the brain works and how it gives the directions to the human and how the human reacts according to that, and how he able to recognize or how he able to identify the particular person, either he may be a father or mother or friend or relative. So like all computers, a brain is also considered as a dynamical system. Like all computers, brain is also considered as a dynamical system that carries out its computations by the change of its state with the time. Brain is a dynamical system that carries out its computation by the change of its state with the time. For example, at time t equal to 0, there is no change in the dynamics of the human brain. At time t equal to 1, the person sees something through sensory organs. What are all the various sensory organs? Through eyes, through ears, through nose, through the other receptors, mechanoreceptors like touch and feel. All those things may be considered as a sensory organs. At time t equal to 1, if the human receives certain inputs via the sensory inputs or via sensory systems, okay, so there may be a change in the state with respect to the time. As time progresses, there may be changes in the states in a given environment where the human receives the inputs via the sensory organs, and through that inputs, the inputs are forwarded to the human brain, and brain accepts those inputs and reacts accordingly. The simple models of dynamics of neural circuits are described that they have a collective dynamical properties. The simple models of the dynamics of the neural circuits. So how the computer works, similarly the neural circuits also works. So the dynamics of the neural circuits are described that they have a collective dynamical properties. So what is those collective dynamical properties are nothing but, so with these properties, so we can exploit, with these properties like registering the inputs via different sensory inputs or sensory organs, and giving directions to the human, and human reacts according to the directions as the time progress or by the change of by the state of time. So these factors can be exploited in recognizing the sensory patterns. So using these collective properties, okay, in processing information is effective in that it exploits the spontaneous properties of nerve cells and the circuits. So that is nothing but it exploits the spontaneous properties, nothing but. So whenever I see a fire, so I need to put off the fire, or whenever I take a cup of hot water, so I feel that it is too hot, or it is slightly hot, or it is moderately hot. That is considered as a spontaneous property of nerve cells and the circuits. So what is the quest for John Hopfield? To make this physical systems to interact, or to make this physical systems to introduce into the neural network domain. So while the brain is totally unlike modern computers, much of what it does can be described as a computation. So what the brain does is nothing but, so brain is ideal in nature. So whenever it receives certain inputs from sensory organs, so the brain tries to accepts that, it tries to process those information, and it gives instructions, and then based on the instructions, the humans may react or the humans may not react according to the instructions of the brain. All these activities in a step-by-step procedure can be considered or can be described as computation. So how we do in a normal computer. So how the brain's function or brain's actions are described as a series of computation. So like it stores certain information in the associative memories. So it thinks the logic, and it works for the inference. It looks for the inference. Then it tries to recognize a odor in the sense, so whether it is a good smell or bad smell, whether from which particular direction the smell is also coming. So whether it is from the front direction or backward or towards the left or towards the side or towards the diagonal directions. So like that, recognizing the odor or recognizing the chess position. So whenever you try to play a chess, so which particular coin has to be placed next, you need to think of the future moves also, and then we need to remember the chess positions. Then the next one is nothing but parsing the words into the objects, like so how we try to segregate the different parts of the globe, like this may be hilly areas, this may be vegetative areas, this may be what you can call as city locations, this may be an urban locations, this may be a village locations, like that, parsing the world into different objects and generating appropriate sequences of locomotor, muscle components, muscle commands, all describable as a computation. So whatever may be the case. So storing it, you have to think the logic, then you need to find the inference, then you need to recognize, and then you need to parse, and then you need to generate the appropriate sequences of actions through muscle commands. All these considered as a computation. So the research focus of Hopfield on understanding how the neural circuits of the brain produce such a powerful and complex computations. So his research focuses on understanding so how the neural circuit of the human brain, so how the human brain receives, accepts, process, and throws some directions or throws some commands to the human in order to execute those tasks or in order to complete those tasks, that is considered as a computations. So his research on that. Then all flexion is nothing but the simplest problem in all flexion is identifying a known odor. Known odor, it may be a scent, or it may be a bad smell, or it may be a good smell, whatever may be the case. So Half-Field has been studying how such computations might be performed by the known neural circuitry of the olfactory bulb and piriform cortex of mammals or analogous circuit of simpler animals. So piriform cortex is nothing but so whether I have a good smell or bad smell, or I have a pleasant smell. So all those things I need to segregate via this olfaction. So this, however, this procedure allows a remote sensing and much more complex computations involving the wind direction and fluctuating mixtures of the odors also. So I may not get a simple odor or a single odor. I may have multiple smells, or I may have a heterogeneous smells will be there. Sometimes I may get good, sometimes I may get bad, sometimes I may get pleasant, or sometimes I may have the combination of permutation and combination of all these mixtures of odors or smell. I need to describe from which particular direction the smells are coming, or from which particular directions the smells are moving from one location to the other location. So all those things I need to find out with the help of this theory here. Next one is dynamical systems. Any computer does its computations by changes in its internal state. There is nothing but whenever I supply an input, or whenever there is a change in the current state to the next state, or probably the future state. So that may be considered as a computation, the movement from one point to the other point. So in the case of neurobiology, the change of potentials of neurons with the time is what performs the computation. Change of potentials of neurons is nothing but the strengths or the excitement of neurons may be considered as a computation. So the systems of differential equations can represent these aspects of neurobiology. So he seeks to understand some aspects of neurobiological computation through studying the behavior of equations, modeling the time evaluation of a neural activity. That is nothing but, so the differential equations also can be used to represent the changes in the behavior of an neural activities, and that may be considered as a neurobiological computations. Action potential computation for any such neurobiological activity, the information is represented by the paradigm of firing rates. Firing rates in the sense is nothing but, as we saw in the initial class, so whether this particular neuron or this particular node in the artificial neural network is responsible or is taking part in the firing process. If it has an excitatory weight values, then it may take part in the firing process. If it has an inhibitory weight values, it does not take part in the firing process. So that may be considered as an action potential computation. So the information is presented by the paradigm of firing rates. That is, the information is represented by the rate of generation of action potential spikes, and the exact timing of the spikes is unimportant. When it fires is not required, but whether it fires or not is important for me. When it fires is not important for me, but whether it is taking part in the firing process, that particular neuron is taking part in the firing process, that is important for me. Since the action potential lasts only for about only a millisecond time, so the use of an action potential timing seems to be more powerful potential means of neural computations. So that firing process lasts only for a millisecond period of time. So that particular time has to be taken into consideration during the computation process. There are cases, for example, the binaural auditory determination of the location of sound source. This is nothing but where exactly, from which particular point I receive the sounds. So binaural auditory determination is nothing but, so I need to utilize both the ears, and from both the ears So where the sound travels, okay, from which particular direction the sound travels. So what is the audibility of the sound? So all those things has to be observed by both the ears. But you see, so whenever you say that the sound travels is observed by both the ears, there may be a slight or very minor lag between one ear to the other ear. Suppose if the sound travels from left to the right means, so you may first have an effect for the left ear rather than the right ear. So it will be little bit delayed, maybe a millisecond or maybe a microsecond, because it travels from left to right means, so first it will be observed by the left ear rather than the right ear. If it travels from right to left means, first it will be observed by the right ear rather than the left ear. So this is nothing but the location of sound source where the information is encoded in timing of the action potentials. So next example is nothing but the speech. So identification of words in natural speech is difficult computational task which brains can easily do. So identifying the words in the natural speech is nothing but, so if you are listening to a complex conversation, or if you are attending a particular seminar where you are attending for more than an hour or more than an what you can call it as minutes and a couple of minutes. So in such cases, what are all the key points that identification by a normal person is very difficult, but the brain can easily understand those things. So they use this task as a test bed. This identification may be used as a test bed for thinking about the computational abilities of neural networks and the neuromorphic ideas. So test bed in the sense is nothing but, so in the application of speech recognition or in the application of speech applications, okay, what we are trying to do here is nothing but, so identifying the words in a natural speech is considered as a difficult task where brains can easily do. So this particular issue or this particular problem is taken as a test bed, and the neural network is trained for the speech processing or the speech applications, and then we try to provide certain type of solutions like speaker dependent systems, speaker independent systems, or word independent systems, or word independent systems. Like that, we try to develop certain applications in and around the speech processing. So we say that it uses a binary logic. Simple neurons are coupled in a system with a recurrent signal flow. So the first example we can see, the two neurons half-wave network of continuous states are characterized by two stable states. So one is considered as, this is one node or one neuron, and this is considered as another node or another neuron. And this you are saying that from this neuron to this neuron, the associated weight values is first neuron to the second neuron, it is nothing but W12, and from the second neuron to the first neuron, it is W21. So both are same, they are saying W12 equal to W21. And this Z is considered as an what you can call it as net input for this particular node. So if you try to plot the two neuron half-wave network, and the plot may be considered as a contour plot. The plot may be considered as a contour plot. And in the second example, you see, we use three neuron half-wave network. So neuron 1, neuron 2, and neuron 3. And with this, it may be given a cuboid kind of an plot. So this may be considered as a stable state, and this is also considered as a stable state. This is stable state. This is stable state, and so it may be considered as a cuboid kind of an plot will be given if three neurons are involved in the half-wave network. The third example, if more neurons are involved, so it says that the behavioral of a dynamical system is fully determined by synaptic weights. So here node 1, node 2, node 3, node 4, and node 5 all are interconnected. But if you see this particular diagram, it looks in a complex nature and it is clumsy in nature. So these nodes are rearranged in this fashion. And if you see this, so N1 is connected to N2, N3, N4, and N5. Similarly, N2 is connected to N1, N3, N4, and N5. So like that, it gives a simplified view of this particular complex structure, and Wij equal to Wji. Wij is nothing but the weight values from node 1 to node 2 for a node 1 to node 5, and Wji is nothing but from node 5 to node n 1. So this is nothing but this one, and this 0 0 0 in the diagonal represents, it is considered as a binary input. It is considered as a binary input, means this diagonal values of the matrix will be converted or will be represented as zeros. And this may be thought of considering as a minimization of energy map over here. So this is the actual architecture of half-wheel network. So half-wheel networks are fully connected, symmetrically weighted networks that extended the ideas of linear associative memories by adding the cyclic connections. So this may be node 1. You see it is connected to here, connected to here, connected to here, connected to here, connected to here. So like that. So each and every nodes or every neurons are fully connected and symmetrically weighted networks extended the ideas of linear associative memories by adding the cyclic connections. By adding cyclic connections. Note there is no self-feedback in this. There is no feedback for this particular net itself. There is no self-feedback for this particular net. So it is considered as a symmetrically weighted network. So the operation of the network. So it have three types of stages. So one, it is considered as teaching. Next is considered as testing. And the next is considered as excitatory stage. That is nothing but your convergence stage. So after the teaching stage, that is nothing but your training, in which the weights are defined. The initial state of the network is set, and the simple recurrent rule is iterated till the convergence to a stable state is nothing but output pattern. So whenever I supply an input pattern, so I need to obtain an output pattern. So until that, so I need to iterate or I need to repeat the process till the network converges. There are two modes of operations. One is considered as synchronous operation, other one is considered as asynchronous operation. So regarding the training of half-wheel network as a content addressable memory, because it belongs to an associative memory kind of network, so we are using the outer product rule for storing the patterns over here. So with this, I will skip this slide and next we will move. Is the slide is visible? Is this visible? Yeah. So we say that it is a recurrent artificial neural network and all those things. The same story is repeated over here. This is fully connected single layered recurrent networks. All the neurons in the network are feedback from all other neurons, and the states of the neurons is either +1 or -1, as we saw in the 2 connected neuron and 3 connected neurons. So you have a ramp kind of an input which represents plus and -1, or we have instead of 1 and 0 in order to work correctly. So no input node should always be equal to, so number of input nodes should be always equal to the number of output nodes. Why? Because we have only one kind of a layer. So x1, so this is y1, x2 it is y2, and x3 it is y3. So algorithm, this is very important takedown. So first I need to initialize the weights to store the patterns. Next step is while activations are not converged. Okay. So here I am trying to apply the activation function. So once here I try to apply the activation function, and I will try to find out whether I can able to get the output or not. If I am unable to get the output, I say that it is not converged, and I need to continue the steps 3 to 9. So for each input vector x, I need to repeat the steps 4 to 8. So set the initial activation of net equal to external input vector x. So yi equal to xi. So whatever the yi, it is equal to xi. Then I need to repeat the steps from 6 to 8 for each unit in yi. So what I need to find out is for this y1, I need to compute the net input here, and then I need to apply the activation function. Here also I need to compute the net input and apply the activation function. Here also I need to calculate the net input and I need to apply the activation function. That's why they say that for each unit in yi, I need to compute the net input yin of j equal to xi plus summation of yj into wji. Determine the activation of the output signal. If it is greater than theta, it is 1. If it is equal to theta, it is same value. If it is less than theta, it returns the false value, and theta always takes the value as 0. Theta always takes the value as 0. So step number 8, broadcast the value of yi to all other units. So if broadcasting the value of means this value has to be broadcasted to y2 and y3, and y2 values should be broadcasted to y1 and y3, and y3 value to be broadcasted to y1 and y2. So I need to test for the convergence. If the network converges, then I say that I am going to stop my iterations. If not, then I say that I am going to continue this process. So take down this problem. Take down, quickly take down. So what is given in the problem statement? So first I need to construct a discrete half-filled network with the input vector 1, 1, 1 and a -1. So what is the problem? I need to construct a discrete half-filled neural network with the input vector 1, 1, 1 and a -1. Also, I need to test the discrete half-filled network with the missing entries in the first component and the second component. So this is first component and this is second component of stored vector. Have you taken the problem? Have you taken the problem?
No.
Make it fast. What is given? The solution here is the input vector x is given as 1, 1, 1 and a -1. Okay. So I need to construct a weight matrix. I need to construct a weight matrix. So weight matrix formula is given by W equal to summation of S transpose of P into T of P. S transpose of P into T of P. Okay. So what is this S and what is this T? What is this S and what is this T? What is this S?
Input and target.
Input vector and a target vector. So this X is equated to S and Y is equated to T. Okay. So X is given as 1, 1, 1 and -1. So the transpose of this row matrix will become as a column matrix. Transpose of row matrix will become a column matrix. And this is nothing but my output. So whatever the target output, whatever my y I am putting equating to a target output. So what is input? I need the same get as an output over here. So 1, 1, 1, -1. So this is 1 cross 4. So if I multiply this 4 cross 1 and 1 cross 4 matrix, so I may get a weight matrix as 4 cross 4 matrix. Is it clear? So I have a weight matrix as 4 cross 4 matrix. Now I am saying that weight matrix with no self connection, that is nothing but no self feedback. In the half field network, there is no self feedback means. So I am considering all these diagonal elements as 0 and I am rewriting the weight matrix like this. There is no self connection between one node to the other, between the nodes. So I am rewriting the diagonal elements with the zeros. So that is nothing but the new weight matrix values with the no self feedback. So now for the EC calculation, instead of taking the bipolar representation, I am converting the input vector. In a binary representation. Instead of 1, 1, 1 and minus 1, 1, 1, 1 and minus 1. I am converting that into a binary representation. So this minus 1 I am replacing with a 0. Is it clear now? Any doubt?
That's clear.
Yeah. Now, in the previous slide, we saw that the updation may be with two types. One is nothing but synchronous type and other one is asynchronous type. Okay. Since I have four inputs, x1, x2, x3 and x4, if I say that if it is a synchronous type, okay, so I need to go like this, y1, y2, y3 and y4. So since I am going to carry out in an asynchronous fashion or asynchronous updation of weights, so let it not follow the same process, but I follow like first I may consider y1, next I consider y4, next I consider y3, next I consider y2. Now what is the problem statement here is, so I need to test the discrete half-wheel network with the missing entries in the first and the second component. So this component x1 and x2, I need to say that missing entries. So missing entries means it is considered as 0. So the first for input vectors with the two missing entries in the first and second components of stored vector, it is 0, 0, 1, 0. Missing entry means it is replaced with a 0, 0. And if it is mistake entry means the positive will be with the negative and negative will be with the positive, as we saw in the auto association and the hetero association neural network. So what is step 0? I need to initialize the weights. So the weights are initialized like the same weight matrix we are taking. Then step number 1. So what is my input vector? Input vector x is nothing but with the two missing entries 0, 0, 1, 0. And what will be my output? I need to get the same as my output y equal to 0, 0, 1, 0. That is why the second step. And third step, I need to choose the unit y for updating. I need to choose the unit y. So here I have y1, y2, y3 and y4. So I need to choose the unit. So what is my order with respect to my asynchronous? First I will go with y1, y4, y3 and y2. So I am first choosing y in of 1, which is equal to x1 plus summation of y I into wji. So which is nothing but so what is my x1 value? Since x and y are same, my x1 value is nothing but this 0. And what is my yj? Yj is nothing but this one 0, 0, 0, sorry 0, 0, 1, 0, this yj. And what is this wj1 means? This first column alone I need to consider. This is wj1. So 0, 1, 1 and 1. The first column I am considering as it is 0, 1, 1 minus 1. So if I do the calculation, it is 0 plus 1 equal to 1. So now I need to apply the activation function. So yin of 1 is greater than 0. So I consider that y1 equal to 1. So my I need to broadcast this y1 value to all the other units of y. So we get y equal to, instead of 0, 0, 1, 0, I get 1, 0, 1, 0. Is it clear? Any doubt? Okay. Next one. There is no convergence. Why? Because what I need to get as 0, 0, 1, 0. But what I get here 1, 0, 1, 0. So the network is not converged. So no convergence. So what I need to do, I am choosing the next asynchronous updation. So Y1, next I have chosen Y4. So choosing the unit Y4 for updating its activation, same process I need to do. So Y4 equal to X4 plus summation of Yj into Wj4. So X4 is 0 plus this Yj is nothing but the new value 1010, and this is nothing but the fourth column of the weight matrix. What is the fourth column? -1, -1, -1, 0. Same thing I am using here, -1, -1, 0. So if I compute, so I may have 0, -1, -1, it is -2. So Y in of 4 is less than 0. So Y4 is nothing but 0. So I am replacing, I am getting the same value 1010. So again, it is no convergence. Next, I am choosing the next asynchronous node as Y3, and I am updating its activation. So X3 plus summation of Ya and Wj3. So X3 value will be, so 1010. So it is 1, and Y value is this. And this is nothing but the third row value 110 minus 1. So I may get as value as 2. It is obviously greater than 0. So I may get it as 1, third value. So again, it is no convergence. Then lastly, I go to the second unit Y2. So X2 plus summation of this. So X2 value is 0 and Y value is this, and Wj2 value is 0, 1, 0, 1 minus 1, the second column of the weight matrix. So I may get 0 plus 2, which is nothing but 2. So it is greater than 0. So it is 1. So now Y value is converged. So what is my input? What is my input? So binary vector representation is 1, 1, 1 and 0. So the same output, I am getting it as 1, 1, 1 and 0. So I am saying that the network converges. This is clear? Okay. So I will conclude here today, and from tomorrow onwards, we go with module number 3. Okay.
Excuse me, sir.
Yes.
Sir, I was absent for the only 2 classes, but I marked absent for 4 classes in the meet of attendance. Can you please check, sir?
Can you please send me the message? I will look into it, please.
Sorry.
Thank you. Okay,
So
thank you.
I have texted regarding the same issue, sir.
You send me the message. I will look into it. Okay, please.
Oh, okay.
Thank you.